Okay, thank you. So yeah, this is the overview for Genesis. So I'm presenting on behalf of the team. I know that a lot of the Genesis team are actually giving full updates. So I've tried to focus on the members or the projects where there aren't any updates in the program at the moment. How do I progress it? Green button? Okay. Other green button? No? Okay, there you go. Yeah, okay, well, slow down. For the new members of ASTRO 3D, I guess the question may be, what is Genesis? And I'm sure it's been apparent in the ether that it has something to do with simulation. So we're the thread within ASTRO 3D that focuses on trying to model galaxy formation and evolution across cosmic time from the epoch of reionization to the present day. And we use a combination of techniques, so big n-body simulations and semi-analytical models. And you'll hear more about those later on from Adam and Claudia. In-house non-cosmological and cosmological n-body hydrosims. We have very close links with our overseas collaborators, for example, Eagle and Illustrious TNG. So we leverage those links to provide data to our community here. And we also do development of in-house software tools. So you will have heard from Kate this morning about SimSpin, which is this amazing tool that she developed during her PhD and is now applying to lots of really cool surveys. The Genesis team consists of the lead CIs, Darren, Stu, and myself. And we have a couple of postdocs at the moment. So Yu Sheng, who's actually chairing the session, so he's going to give me lots of extra time. And Manadeep, who's based at Swinburne. And we've got a pretty big team altogether, but they're mostly students. Yeah, it's we're doing a range of work. So just to focus on a couple of the, oh, that's unfortunate. So I'm sorry, Angel, we didn't mean to get involved there. So we're doing a range of interesting projects, and Angel is a good example. Angel just started his PhD at UWA a few months ago, and he's working with Claudia Legas and me, looking at the formation of massive galaxies across cosmic time, and in particular looking at high redshifts, trying to make sense of the predictions, or trying to make sense of what we're seeing for JWST. So one of the things that Angel's been doing is trying to look at how well the merger trees that we use as an input for the SAMs are performing. And if you look up in the top, from your perspective, the top left-hand corner, there's a plot there showing the growth of a halo from across snapshots, but that's basically tracking redshift. So you can see that the halo mass growth over time. And you'll notice that relatively late times, big masses, there's a big dip occurring there. And this is a problem that we find, and it's a fairly generic problem within the merger trees, that you get so-called halo swapping. And it arises because of the way we do the merger trees. We're trying to track bound material across cosmic time, but that's not always the best way to do it. And so as an example, here's a figure from Strisawat 2013 that highlights the issue. So as you go from left to right, you can see the main big circle changes color at snapshot 60, the second from right from your perspective, and it changes red to blue. And that's because there's a confusion within the halo finder about how to link. And so this is actually quite a thorny problem, and Angel is throwing himself against it with gusto, and we should make some progress soon. So keep an eye on what's happening here, and we'll have some cool results coming out soon. This is a new project, work in progress by Balu, based over at Melbourne. He's a final year PhD student. So Balu is going to be giving a talk tomorrow, maybe? Yeah, today, okay. Yeah, I should pay attention to the program. So he's going to be giving a talk on the EOR, all the nice work he's been doing with that. But one of the things he's been doing over the last several months has been looking at where might we look for the first stars. So he's been getting experience running his own Zoom dark matter simulations of Milky Way mass halos, and trying to place limits on where we would expect to find the earliest star forming regions. And so from your perspective, if you look on the left-hand side, this is showing a density profile as a function of radius. So the blue curve shows the dark matter density within the system at redshift 0. And then you have a range of different curves, orange through to magenta or purple. And that's showing the material that Balu has tagged as material that was part of like a halo at redshift 5 through to 12 that could have potentially formed stars because it's above the mass threshold for atomic line cooling. And the interesting thing is, how can we actually detect this in the present day universe? So if you go to a Milky Way mass halo and look at the phase space diagram, which is shown on the right-hand side, this is showing how the kinematics of the material. So the blue corresponds to the halo material, the main halo material, and the orange points correspond to the bound material within these collapsed halos. And you can see that there's potential here to look for structure and phase space and potentially put limits on where the first stars are. So this is work in progress, and over the next several months, hopefully we'll get some papers out on this. This is a really cool project by Adam Ussing over at Swinburne. And Adam's trying to ask, how can we use dusty galaxies to tell us about dark matter? So why should there be any connection between dust in a galaxy and dark matter? Well, the reasoning is that the amount of dust in the galaxy will reflect the extended period of star formation within the galaxy. And so if you have a difference in when these galaxies formed, you might expect to see different amounts of dust within the galaxy itself. Sure, there are caveats there, but it's an interesting experiment to do. So from your perspective on the left-hand side, Adam was trying to figure out how to match systems across the different dark matter models. And so the focus was on trying to get a fit for the satellite population of a Milky Way type system at redshift 0. And this allowed him to quantify the parameters within the models. Okay, so he was able to figure out exactly what galaxy formation parameters he should be using. And then if you look on the right-hand side, the two color barred plots show the distribution of gas mass and dust mass within those galaxies. And then on the far right side, you've got the difference map. So that's telling you where the main significant differences are. So this is still work in progress, but Adam's doing some nice work in this area. So if you want to find out more, go and chat to Adam afterwards. Shifting tack a little bit, this is a project that I've been involved in with our affiliates at the University of Tasmania, Patrick Yates-Jones and Stas Shabala. And the idea here was to try and understand how well we can make predictions for jets in cluster environments. And so there's a kind of a dichotomy within the simulations community. There are people who do jets and there are people who do cosmology, and sometimes they cross over. So we do try and model jets within cosmological simulations, and I should get that right because Lars is sitting in front of me. But the point is that when we model jets within a cosmological simulation, we're doing it in a very crude way, in approximation. And so what we try to do here is take results from a cosmological simulation from the 300, which was a galaxy cluster, and see what happens when we let a jet propagate within this within the system. And the interesting thing is to look at the effect of cluster weather. So these are some plots here just showing what the density distribution is of those jets. So you can see jets on the left-hand side showing the density, and the up corresponds to the jet axis. And these are all measured at the same time. And these just correspond to different ambient densities and jet powers. And this could be then converted into radio maps. So these are surface brightness maps available via a Cosmo Dragons app that has been, we're working with ADAX to do. Now, a really interesting outcome of this work, so that was basically just a presentation of the data and that it works and it looks sensible. But this is a really cool project that Larissa Jerem has been working on. She's one of Stas's students. And the idea here is to actually figure out how can we use information that we can measure in radio to tell us something about the ambient conditions within the jet. And so on the left-hand side, on the upper case, you've got the jet in density. On the bottom, it's showing what the magnetic field is doing. And what's happened here is that Larissa has propagated a jet into a turbulent magnetized medium. And so we can then create surface brightness maps, and in particular, we can make rotation measure maps. And so the really interesting thing about these different maps is that the rotation measure that we can actually measure depends on the ambient density, but also on the magnetic field strength. And so by making these kinds of maps, you can start to break the degeneracy that exists between the size and luminosity relation that we see for these kinds of systems. And so it's a potential impact, it's a potential metric of the impact of jet power. So I couldn't find a nice picture of Nick. So here is, he's doing a handstand at the UWA gym. But Nick is working with me and Stas and Martin Bourne in the UK, and also Aaron Ludlow here at UWA to try and get a better, to try and come up with a score sheet for how we model jet feedback. And so the idea is we can take different codes. We can take a code like a repo, which is a moving mesh code. We can take a code like Gadget 4, which is a traditional SPH code. And we can also take the kinds of codes that were used to run those dedicated jet simulations. So in this case, it's Pluto, which is an AMR run. And we can look to see how well those different codes perform at recovering the solutions to known kind of simplified solutions. So for example, in this case, Nick is showing the density, velocity, internal energy, and pressure as a function of position along, as a function of radius for the so-called setup blast wave, which is a kind of it's an analytical approximation to what we would expect for a supernova blast. And so what we can see here, gratifyingly, if you're an Arepo fan, is that Arepo does a much better job of capturing the structure within the shock. And that's not unexpected, but Nick is now doing the same kind of exercise for stellar winds and for jets. And so he'll have some nice metrics for how well these different codes perform, and we can then apply it into galaxy formation simulations. This very quickly is Andrew Sullivan's work. So we heard from AJ earlier about the work he's doing on trying to estimate halo mass. Andrew is a hardcore theorist in the sense that he does like to do pen and paper calculations and really doesn't like to do simulations very much, and that's fine by me. So he's been looking to understand how he can come up with an analytical approximation to the temperature profile and the density profile of baryons within a dark matter halo. And so he's been able to experiment with different kinds of dark matter backgrounds and different approximations about what the gaseous conditions are to come up with prescriptions that could be coded up analytically. And so from left to right, these are a bunch of different temperature profiles as a function of radius. The different curves correspond to different inner slopes. The filled squares correspond to some observational data from Vicklinen et al. 2005. And you can see that this, even though it's a purely analytical scheme, it does a pretty good job in some cases. And so this is allowing Andrew to start building a framework to examine real data. And finally, I'm guessing Kate presented this earlier, but just a reminder that SimSpin is now out and it's doing wonderful things. Okay, I will leave my slide up and then take questions if there are any. Thanks.